This is problem 24 of the QHack 2023 Quantum Coding Challenges, and this one is entitled Sky Trotter. In this problem, we're being asked to implement a unitary u of t for some given Hamiltonian h, which is given by this expression, and we are to construct that unitary u by using the process of Trotterization. So let's go ahead and go step by step and describe what this all means. So the first thing we're reminded of is that the evolution of a quantum state psi is given by this equation here. So basically we have some initial psi of 0, and that psi at some time t is evolved by some unitary that depends on the time. And that unitary, surprisingly, is given by this expression. So it's the exponential of some Hamiltonian, and the Hamiltonian is the energy operator or observable of for a given system. And then we know that in general, this Hamiltonian h can be the sum of different terms. So in that case, that unitary u of t is now the exponential of minus I times that h1, h2, and so on and so forth. So all the different terms this Hamiltonian can be composed of, times t or h bar. H bar is just Planck's constant divided by 2 pi. Now the question is, how do we implement this unitary u of t given some Hamiltonian? So the first thing to remember is that if we have an exponential of the sum of two real numbers, that is equal to just basically the exponential of one of those numbers times the exponential of the other number. Now the problem here is that these Hamiltonians, h1, h2, and so on, are matrices. So for matrices, this rule of exponentiation of the exponential of a plus b being equal to the exponential of a times the exponential of b only holds true when the matrices commute. So basically when a times b is equal to b times a. But in general, that is not the case. Matrices not always commute. So what do we do in the general case when this a times b is not equal to b times a? We use what is known as Trotter-Suzuki decomposition. And that's just an approximation in which the exponential of some matrix A plus B is given by the multiplication of the exponential of the matrix A divided by some number n times the exponential of B divided by n, and then we repeat that n times. So basically we keep multiplying these exponentials over and over again, and then this equality holds as n tends to infinity. So what we can do to generate this unitary u of t is that we can use this expression to get an approximation of u of t. So basically what we do is, given this u of t of the exponential of the sum of some Hamiltonians, well, we can do the exact same thing we did above here, but for this Hamiltonians, right? So we have now the exponential of h1, h2, and so on. And then we repeat that n times, and then that's the same as applying a unitary u1 of t divided by n, u2 of t divided by n, and then we repeat that n times. And now if this n is finite, then this is not going to be an equality, but it's going to be approximately equal. And as we increase that number n, then we get closer and closer to a unitary. Now, in terms of a circuit diagram, this is just basically saying that this unitary u of t is approximately equal to implementing the circuit where we apply u1, u2, all the way to u sub m. So given some m number of summation terms in that Hamiltonian, and then we repeat that n times for the Trotterization process. All right, now for this problem, what we're given is the following Hamiltonian. So we're told that h over h bar is this alpha times the tensor product of xx plus beta times the tensor product of z and z. So basically we just going to do the exact same thing. To compute this u of t, we just need to apply Trotterization. So we're going to do the exponential of minus I times the first term of the summation on the Hamiltonian we're given, right? Times the exponential of the second term. Now, luckily for us, this Hamiltonian where we have this xx term and this zz term is a very common gate in penny lane that's called the Ising XX and Ising ZZ gate, which if we look at the definition, let's say for the Ising XX gate, we see that an XX of phi is given by this exponential of phi over 2, right, times minus I and then XX. So in order for us to match that definition to what we're given here for, let's say, this first term, which is just alpha XX, then that means that the argument of that gate needs to be 2 times alpha times t over n. And then what we need to do is apply these two gates, XX and ZZ, and repeat n times. So let's go ahead and get that coded in penny lane. So we're going to import penny lane and numpy. Then we're going to define our device for 2 qubits because we have those Hamiltonians with 2 terms. And now define our Q node, which we're going to call Trotterize. That's going to take as an input alpha, beta, the time, and the depth. And this depth is basically that term n we've been discussing. So the number of repetitions of the multiplication of those exponentials. So then what we need to do here is define our Ising gates. So we're going to do the Ising XX. And as we said, 2 times alpha times the time divided by depth. And then that's going to go on both wires. And then the exact same thing for the Ising ZZ, but here we're going to use beta. Now, because we need to repeat this n times or depth times, we need to put this into a for loop, right? And that way we will apply these 2 gates depth times. And then what we're told is just to return the probabilities of this circuit, okay? And now we have 2 inputs here that are given to us, and all we need to do is just print this Trotterize function with, let's say, input 1, and here we get 0.9900 and 0.0099. So if we go here and look at the result that we're supposed to get for the first input, that's exactly what we get. And then for the second one, we should get 0.8700.124. So we can now check that for that input 2. And then we get the expected answer. So as always, I hope this was helpful. Let me know if you have any questions.